Look, I told you, it doesn't matter why I want it or how much it costs. Just get me that space car and do it. Do it!
Let's just say that for some supervillainy reason, you wanted to steal the only sports car currently in space. How would you do that? Let's get technical.
Get it to me now!
In early 2018, a one Elon Musk, after taking suggestions on Twitter, decided to christen the launch of his Falcon Heavy rocket with the silliest thing that you could imagine. That silly thing just happened to be his personal Midnight Cherry Tesla Roadster. After launching in February, that road car became the first in the cosmos, carrying a towel and blasting David Bowie. It was a heck of a spectacle, sure, but the car isn't just lost to the void now. We know exactly where it is. All an enterprising supervillain would have to do then is get to it. And I'm not saying I'm one of those, or that you should do it. I'm just saying this is how you could do it. Very, very important distinction there. First, it's not like government agencies or Musk himself is going to help us nab a space car that's already traveled the equivalent of 37 times all of the world's roads put together. No, so we're gonna have to take a quick crash course in orbital mechanics and maneuvers. Probably not the best choice of words there. And don't you worry about how we're actually going to intercept and then return the Tesla to us. I so happen to have a Tesla capture device that I found at a yard sale. What we really need is a plan and a pathway through space. When should we launch? How long will it take us to get to the Roadster? What will the trajectory look like? Ooh, it's all coming together, he said innocently. A rendezvous in space isn't as easy as just pointing and thrusting. And that's because everything in space is moving. Gravity is everywhere and it affects everything, and so in effect, everything in the universe is always falling around something else, whether that be the Earth around the sun or a galaxy around another galaxy. And so any orbital maneuver inside of our solar system, for example, has to take into account this omnipresence of gravity. For example, if you wanted to launch a rocket from Earth to Mars and you just point and shoot without gargantuan thrust, you're gonna miss. So instead, bending to gravity's whim, we're gonna wanna take some kind of curved path, not a straight one, that will take us not just to where Mars is, but to where Mars will be when our rocket gets there millions of kilometers later. This kind of orbital maneuver is one of the simplest and easiest in terms of fuel, and it's called a Hamann transfer. So we're gonna wanna learn the mechanics of this kind of transfer if we're gonna pull off Grand Theft Stratosphere. Strip. So let's learn by doing and return to the example that we just laid out. How would we really get a rocket from Earth, where it would launch from, to Mars, where there's definitely not a subterranean base of mine, for sure? We know we have to take some kind of curved path again, but we have to be exact or else we're going to miss Mars, where something is definitely not being constructed right now. Don't even worry about it at all. So let's get more technical. The idea during a Hamann transfer is to take some kind of elliptical path to your destination, but when you get there, you have to remember that a celestial body or a planet or what have you has a lot of velocity on its own. So when you get there, you're gonna have to match that velocity in some way. And so this kind of maneuver won't just take one burn to launch you off of a planet like Earth. It's actually gonna take two. One to launch you off of your planet, and then a second to match the new orbit of the thing you are trying to intercept. When performed correctly, this kind of maneuver looks like this. This is NASA launching their InSight mission. It looks relatively straightforward and easy, but it only looks that way. There's actually a lot of math involved, so if we only have really probably one shot of stealing Starman, we're gonna learn the math behind this kind of transfer step by step. Oh, I'm gonna let that go to voicemail.
Answer me, you coward!
Just how much velocity do you need to add to or subtract from a rocket in order to get it to Mars or even a space car? That's right, it's space enthusiast pop quiz time. Here is the Sun and Earth and Mars in their respective orbits. I'll lay out all the variables that we want. To get from the Earth to Mars with one of the simplest transfers that there is, we're gonna have to know the orbital velocity of Earth, the orbital velocity of Mars, and the velocities that we need to both enter and exit our transfer elliptical orbit. The force keeping Earth and Mars in orbit around the sun, gravity, can be modeled like the tension in a string if you tied a rock to the end of a string and was swinging the rock around in a circle, but you can also model it like a simple gravitational interaction. So, you can use these equivalences to solve for the orbital velocity of both Earth and Mars around the sun. If we take Newton's gravitational constant as g here, the big M as the mass of our sun, and r being the distance between the sun and the planet that we're concerned about. Now, I was not joking about a pop quiz. What is the orbital velocity of Earth around the sun? You can look up Newton's gravitational constant, the mass of the sun, and the distance from the Earth to the sun. Now, don't just look up the orbital velocity of Earth. I want you to really try it. It's empowering. You can pause the video right now. I'll wait. The correct answer, if we round, is B, 30 kilometers per second. That's how fast the Earth is going in orbit around the sun. How'd you do? Using the exact same reasoning, look up the distance between the sun and Mars and solve for the orbital velocity of Mars. I'll wait. The correct answer is 24 kilometers per second around the sun, C. How did you do? Did you get it? Because now it's time to get a little bit more complicated. Shh, just say I'm not here.
I know you're there!
If you wanted to find out the total amount of energy of a body orbiting something like a star, you would need its energy of motion, its kinetic energy, and you would also need its gravitational potential energy, which is the same energy as anything has sitting in a gravitational field. Anyway, the total amount of energy of an orbiting body is also equivalent to half the gravitational potential energy at the average distance between two bodies. And this is really important because this will enable us to calculate how much velocity we will need to both enter and exit an elliptical path between 2 points. We can use this relationship to solve for velocity here too, and we get the velocity that we need to both enter and exit our elliptical transfer orbit, based on r being the distance between the sun and Earth and the sun and Mars. And remember that a here is those distances added together and then divided by 2. Pop quiz! Using the distance between the Earth and the sun as r first, what velocity do we need to initiate our transfer orbit? The correct answer is A, 33 kilometers per second. Did you nail it? I bet you did, you nerds. Now use the distance between Mars and the sun to find our exit velocity. Pop quiz! The correct answer is B, 21 kilometers per second. Did you get it? Because if you did, that deserves 1 gold skull. We don't give out stars for this kind of mission. So now that we know all of our numbers, what is the total amount of velocity that we need to give our rocket to make it from Earth to Mars? This is a critical calculation in any orbital maneuver called delta V. Pop quiz, what is it? We want the absolute distance between all of these velocities. How much velocity will it take us to launch off of Earth to get us into that elliptical orbit, and then how much will it take us to speed up or slow down to exit from that orbit and match Mars's orbit? Take a shot at it right now. I'll wait again. Did you get 6 kilometers per second? Well, let's check our work. You can find delta V maps for real interplanetary travel pretty much anywhere on the internet. So if we look at the pathway you would need to take in terms of velocity from Earth to Mars and you add all those up, what do we get? Well, I got 5.7 kilometers per second. Look how close we were with 6. We calculated a space mission kinda. That deserves 1 gold skull, maybe even 2 kinda. Yeah. We did the basic calculation, sure, but to steal a space car, we might need some help. We already know the Tesla Roadster's exact location in space. We also know that it's going 40 times faster than a Bugatti Veyron. Thanks to the laws of physics, we should be able to accurately track the position of this space car for centuries. Now, while we could do the same kind of Hammond transfer calculations that we just did to get to this space car, as you can see, the orbit of this car is not quite as nice and circular and centered on the sun as Mars is, so I'm not not gonna lie, these calculations we just went through aren't really gonna cut it, and the math would be a little bit above our pay grade. So instead of going through a bunch of complicated math and then getting it wrong, why don't we instead play around with a very specific and specifically helpful calculator? Sup nerds, welcome back to another Let's Play, of course. Today we're checking out Planetary Transfer Calculator, which you can go and check out at transfercalculator.com. As you can see here, we have the orbits, the standard orbits that we're looking at here. We have the Earth orbiting around the Sun, and we have Mars orbiting out around here. And what's cool about Transfer Calculator is that you can actually add other minor bodies, and we can add Starman. So let's turn that on right here. So now we see Starman's orbit in red. Now what this calculator does is make hundreds of Hammond-like transfer calculations and iterates them down to find the simplest, best transfer, the lowest energy transfer from anywhere you want to go to another place. So we can actually now calculate our path using a lot of mathematical help from the people who created this, our path from Earth to, let's say, the Tesla Roadster. I'm going to set the time to when I'm filming this Let's Play, as we always do, streaming. Yeah, am I right? So I'm going to set the time to now, and then I am going to go ahead and calculate our transfer. I get, if we launch next February, which is the best time to launch according to this calculator, it looks like it will take us just about 16 and a half months to intercept the Tesla Roadster, and then it would take another 16 and a half months to get back to Earth, presumably, and with a delta V of about 4.5 kilometers per second. So this is a much longer transit time, as you can see here, to the Tesla Roadster than it would be to Mars, but it's a much lower delta V. So with all of these numbers, we should be able to set our supervillainy plan in motion. This is all we need. We can see the ship coming within intercept range of the Tesla Roadster now in just a couple months' time. It's pretty cool. I like Transfer Calculator quite a bit. All right. Bearcat comes in with a $5 donation. Hey Kyle, Discount Thor, you really did a great job. Discount. If we use this specific trajectory within a few years, we should be able to get our hands on the only road car that has ever existed in space. And when our undisclosed Tesla Capture spacecraft lands, we will have an awaiting semi-truck to whisk it away to supervillain auction. Of course, we probably won't be able to make back even 1% of the mission cost from the car's sale, but hey, it's the supervillain principle of the thing, which I'm not, and I'm not saying you should do this, and don't tell Elon. So if you're a supervillain and you have millions of dollars burning a hole in your pocket and staff and infrastructure and rockets and a knowledge of orbital mechanics, there is a relatively simple trajectory towards carjacking the Starman. And if you do pull something like this off, not that I support or condone it, tell him it was because science. Space car! You know what might actually be more impressive than a supervillain stealing a space car is if Elon Musk did all of this himself. If he launched it into space and then with his reusable rocket technology in a couple years was able to successfully return a space car back down to Earth, and then he restored it, and then he was driving it around headquarters in Hawthorne, now that would be impressive. And it would prove his rocket technology, and I guess I just gave him a great idea for some PR. You're welcome.